we will kick it off. So thanks for joining today, wherever you're joining from. Hope there's some rain coming shortly in your area, or how far you're into your program. Yeah, as I mentioned just before, a lot of challenges this year with access and cost of fertiliser due to global disruptions. And so, yeah, we want to deliver some information that can be useful for growers and agronomists alike. So I'll hand over to Bruce Armstrong, Senior Nutritional Agronomist from Hybrid Ag, and away we go. Thanks, Bruce.
Thanks, Dan. We'll get this slideshow up and running. Yeah, thanks, Dan, for getting us together. It is a tricky subject at the moment. The whole nitrogen market is a hot topic, I suppose. So what we're really aiming at in our hybrid ag farming systems model is to be more efficient with inputs, aiming at profitability, and nitrogen is obviously a big one of those factors at the moment. Making sure we get the best out of our dollars spent on nitrogen fertilizer, whatever the form is. So quickly today we'll touch on I guess the science behind nitrogen fertilizer and how it's taken into the plant, but also some discussions about different forms of nitrogen fertilizer aimed at efficiency and really ultimately aimed at profitability. So nutrient use efficiency, or nitrogen use efficiency in this particular case, is what we're focused on. The calculations on effective use of nitrogen, as we say, they're worse than what you think. The losses are anywhere from, according to the GRDC in Western Australia, anywhere from 10 through to 75% losses from surface applied granular urea forms of nitrogen. So that's a big scope, it's a big window, but it's also a fair bit of room for improvement. Here's a bit about me, farming as well as providing agronomic assistance through the Hybrid Ag company. Been farming for all of my life in broadacre, in some pasture country as well, some irrigation, and I suppose really focused on soil health and on the benefits to our production system that can be made by improving soil quality, again, based on generating a profit rather than just making soils better. Nitrogen use efficiency, yes, it's worse than we think. Losing a product that's expensive is no good for anybody. That probably goes without saying. That's pretty straightforward. Skip through here. What can we do about poor nitrogen application, essentially, or plant uptake? The idea of pre-drilling products to reduce surface losses, of pre-spreading product, particularly ammonium sulfate. We use quite a bit of ammonium sulfate in our programs in the right soils, of course. Ammonium sulfate is 21% nitrogen, 24% sulfur, but the most important thing there is the ammonium form of N. Use some liquid products as well, so essentially urea in a liquid form applied onto the leaf or in furrow. Obviously ground spread options, and then foliar options for touching on I suppose trace element nutrition, as well as those cofactors that are helping with nitrogen assimilation. James will touch a bit more on those cofactors further on in the presentation. Here's a bit of a snapshot of some when things go well. This is durum wheat again. James will touch on this a bit further on in the program today, but a program based on nitrogen, particularly in this case in the ammonium sulfate form, and then in the calcium nitrate form, but no granular urea applied post-emergent in this crop, which, as Jimmy will get to, yielded over 9 tonne to the hectare in an irrigated system. Different forms of nitrogen there, just a quick science lesson. There's obviously amine, which is the NH2, ammonia, NH3, which is quite volatile, ammonium, NH4, which tends to bind to the soil and stay stay where it's put within reason, and nitrate, NO3, is your quickest uptake into the plant. Can be leachable as well. Fair bit of blurb here about the urea reaction in soil, but probably the main thing I wanted to touch on in here today is the very bottom line, essentially that nitrification that can happen. So a conversion of nitrogen in the form of urea runs through a phase of nitrite, which is 2NO2 in the soil, which in a waterlogged environment or in a compacted environment, that nitrite is not useful for plant function. In fact, it's toxic in that form, and it's essentially denitrifying. It's losing that nitrogen from the budget. So of course, it goes without saying, when it's expensive, you don't want to lose any of it, and you certainly don't want to have it reducing plant benefit. We want to be focused on, in that case, allowing oxygen into that root zone to improve nitrogen conversion into the nitrate form, which is then available for plant uptake. Simple one here, the old Albert Einstein theory. If you can't explain it to a 6-year-old, you probably don't understand it yourself. This is really simple graphic of surface applied urea with the potential for loss to the atmosphere in the ammonia form, NH3. Both are taking place in a urease enzyme conversion. So urease inhibitors are sometimes used to slow down that urease conversion, which is seen as a slow release form of nitrogen from granular urea. Not really what we're on about in this case. Incorporated urea, so pre-drilled. If you're going to use urea, if it's under the ground, it's a safer place to be. The ammonia converts to ammonium in that subsoil environment, and we have a better plant uptake, especially later in the season. We don't see the early vigor from those ammonium levels in the root zone, but better root growth, and then later season accumulation of that nitrogen to finish a crop quite well, which we'll see in the data that we get to. That's the ammonium reaction within the plants. Don't really think we need to go there today. So ammonium in the soil itself still relies on bacterial conversion. Does run through the nitrate phase as well, which is the NO2 in the middle of the page there. And then from a nitrobacter conversion again, with access to oxygen, would become nitrate, which is highly plant available. So hot topic at the moment, foliar urea, or essentially more targeted nitrogen applications as a foliar. Sometimes this is criticised, I suppose, or there's a lack of faith in how this system will work. Will nitrogen be taken up through the leaf? The answer is yes, it can be, as long as the form is right, as long as the application timing is right, and that we don't want to overdo foliar nitrogen applications in big numbers. We're never going to apply bulk nitrogen numbers through the leaf, but does it work to achieve an outcome in terms of nitrogen input through the leaf? Absolutely. Plenty of proof of that, and growers who are happy to testify to how well that system works, combined with other micronutrients, other plant stimulants, and in some cases with a herbicide pass as well. I think that's it.
Yeah, cool. Thanks, Bruce. Yeah, if there's any questions, feel free to turn your mic on or chuck in the chat there. One from me just around foliar application, Bruce. Like, I know it's different needs for different crops, but when you're talking about what we're putting out, what sort of rates is it? Like, is it 15 kilos, 20s, 30s, that sort of rate?
Yeah, it depends on the crop. Depends on the biomass that's there at the time as well, Dan. So if we're looking at a dryland winter wheat, for example, with 4 to 5 tonnes to the hectare of biomass later in the season, say in August or September, to apply 25 units of nitrogen through the boom spray is doable. Western Australians obviously are pretty big on UAN in that situation, urea ammonium nitrate, and their application rates in a normal season get expensive and risky, but in a season like this where prices have effectively doubled, I think we're going to see a reduction in application rate and not see such a reduction in effective yield production from those lower rates applied. So you can go overboard, and they know how to do that and look the other way while the crop goes yellow for a couple of weeks. The result is it works. People are using UAN in that environment because it works and it's cost efficient.
Anyway, yeah, so I'm James Jimmy, and I'm based out of Wangaratta. I head up to Wagga a fair bit as well, from a pasture background in cattle and sheep, bit of wool towards Barnawartha. And we got into hybrid ag by using them on our own farm, actually, and that inspired me to go and study agriculture at Charles Sturt Uni, and been in the job for a couple of years now and quite enjoying it. So I wanted to talk about stacking the benefits and the simple additions that you can put with your foliar nitrogen and other components of the program to enhance your resilience for the soil and root exudates, which then lead into our carbon fixation and sequestration going down the track. So to do that, we'll touch on differential sap analysis and nutrient mobility, different nutrients and how they move through the plant, and how we measure and generate a recommendation based on that. Therefore, increasing plant root exudates and developing a program from that. So that's good. Yeah, a bit about me again. Soil health focus, trying to reduce nitrogen use in cropping from a profitability and a soil health perspective, and seeing some good results on farms over the last couple of years. And I've recently bought my own farm just last year as well, and having a play around there, which keeps it real. So we'll whiz through this a little bit, Bruce. The test don't guess basis, we're using a Novacrop differential sap analysis, which gets sent over to the Netherlands actually. And even though our results take a week and a half to 2 weeks to come back at times, the test itself will predict 3 weeks in advance the deficiencies that could be oncoming. And the way it does this is it's testing what's inside the vacuole of the plant. So that's the elements that are available at the time it's growing, rather than what's already locked away in the cell wall. And the trouble is when you do a dry ash test, you can get false highs because some of those elements are not going to mobilize into the new growing points. For example, there's a bit of a list of the deficiencies that we can see along the way. And boron, calcium, they appear first in the youngest leaves. Our mobile nutrients include the sulfur, manganese, copper, iron, zinc, and molybdenum. And we've got some other ones that are key drivers, our key growth elements, particularly for photosynthesis, our nitrogen, phosphorus, potassium, magnesium. Magnesium being the center of our chlorophyll molecule. I talked a bit about why the youngest mature leaf is inadequate, but essentially it's the nutrients are relocated from old leaves into fresh leaves as the deficiency unfolds, and by stacking them together, we can see where that nutrients are flowing. This is a bit about how we do it. This is, for example, potassium. If we had a youngest mature leaf test, we would have tested within the desired values. Whether here we've sampled the 2 sections, and we can see it as an oncoming deficiency. The new leaf is dragging potassium out of the old leaf as it continues to grow. So in cases where we have soil moisture, that may correct itself. Potassium is a mobile nutrient within the soil, but as we come into the back end of the season, potassium has a greater demand within the plant, particularly for cereals. And as the soil dries out, that potassium becomes less mobile as well. So that's where we're often apply foliar potassium, increasing your nitrogen use efficiency at the back end of the season. This is what our report looks like. 23 different aspects on plant nutrition. We got the major elements. We split up nitrogen, which we'll look at in a couple slides, and some of the trace minerals and troublemakers associated with low pH or alkaline conditions and anaerobic soils. Another benefit of these sort of tests is it gives you an early detection of plant stress. You mightn't have insects in a crop yet, but you would be able to predict the chances of getting insects or fungal infection going forward, particularly as those conditions become more conducive. These are just more examples going through. Same with calcium. The difference with calcium is it's an immobile nutrient, so it's one that will lock up within the cell wall and therefore create a reverse differential. So there's different ways of reading each element is the essential message there. So we'll just skip through these ones a bit more. This is nitrogen. In this case, nitrate is low. We do want a little bit of nitrate for vegetative growth. It stimulates a auxin response in the plant, which is the advantage of combining a nitrate form of nitrogen along with a dissolved urea. Often if you put dissolved urea on its own, you'll be providing energy, but you don't generate the same biomass that you would get with ground applied urea when it takes up nitrate through the soil. So if we can apply both forms as a foliar, you're being both efficient and generating a similar response using less nitrogen. The key part of that is to ensure total nitrogen is converting through. We want to maintain total nitrogen, which is our amino nitrogen, and forms our proteins. That total nitrogen is what insects and fungal infection cannot digest. What they feed on is the smaller nitrogen elements, being ammonium and nitrate. So we want to keep them converting through the plant. And as we go through these tests a bit more, Bruce, might skip through this one, I reckon. That's these outright deficiencies. Some of these trace elements that are critical for conversion are boron, copper, molybdenum, and moly is important, particularly for the conversion of nitrate into total protein. So we can measure that as it flows through. And I've got a slide below a bit further down as an example of what happens when you get a bottleneck. So that's a review of some of these testing methods. We'll probably do about 3 of them within a season, one early tiller, one mid to late tiller, and then before going into grain fill. And that gives us time to collect data throughout the year, and we'll often base the recommendations the following year early on off last year's data, and then follow those tests through to fact check what we're doing. Essentially, doing these sort of tests and applying foliar products, we're trying to generate our liquid sunshine going into the roots, which is what the Loam products aiming to help with as well. The root exudates are in a very usable form. It's essentially a KFC drive-through for the microbes. And the root exudate pathway allows for carbon sequestration deeper down the soil profile, protecting it from oxidative and microbial decomposition. So if we look at an example up the top here, organic residues, you're only getting 5 to 10% humus formation, whether if we really crank that process up within the plant, we're getting 40 to 70% of those sugars converting into stable carbon. So our job as agronomists is to try and get that plant to produce as much sugar as we can to then feed that biology that we're putting with the seed, for example, Loam's product. This is one of the wheat trials Bruce was touching on. It's a little bit blurry, but I'll just walk you through it. There was a a greater spend per hectare with our nutrition program. This is based a couple of years ago, back when urea was $800 a tonne, which is nice as well. However, we've cut back on our urea use in this program, so I would think it stacks up even better now. So the spend was an extra $42 to the hectare. The yield increase was 1.67 tonne, and at current wheat prices, that might be $300. That's still a $500 bonus using less units of nitrogen. And those units of nitrogen were, again, cal nitrate, your conversion foliars I touched on, boron and moly, and some power N, which was a dissolved urea form with some fulvic and sugars, which help that nitrogen convert into total nitrogen faster again. And that was just compared to straight ground applied urea. We'll go to the next. I've had a couple of clients last year that used one of our seed treatments called Precede, and Precede is a fish kelp fulvic dressing, essentially, with added trace elements and a microfeast type product. So that'll feed the biology that you put with the seed. I find it works well with Nutrisoil. It would work well with loam. We often use a trichoderma and a bacillus as well. The trichoderma will embed itself into the wheat plant and help prevent early rust formation as well without using a vibrance or something like that. This is an example of the early results in the field. So as you can see, as long as a CRC can for the roots, on the left here in the middle picture, there was treated with vibrance versus Precede and some Nutrisoil. The coleoptile was much stronger. So you could grab that coleoptile and flick it around. The one that was untreated would actually break in your hand, where the other one remained strong. And that side of the paddock that didn't get the treatment also got those earth mites early in the paddock when we had that frosty conditions last year in a dry season. This is an example of how you could applicate it. There's an inoculator where you're spraying it onto the seed. Otherwise, you can pour it up an auger. And in that case, it's not going to be entirely accurate, but as long as it's coming out wet to touch, it will then imbibe that product later on. And the old saying, I'd rather be roughly right than precisely wrong. So better off going on in some form rather than not at all. This here is an example over in Hopefield as well, just near Corowa, where we use humic coatings and carbon fertilizers. In this instance, ammonium sulfate, like Bruce touched on, still using some MAP for our soluble phosphorus, particularly as the conditions cool and microbial activity slows. We want to keep that active energy going through to convert our nitrogen that we're applying as well. But in this case, where we had a dry year, we're maintaining more of that soil moisture on the right of the picture, and the oats on the left that was treated with straight MAP Senest earlier on. That was good to see in a strip trial like that as he went around the headlands. Here's an example of what it looked like under the wheat. So we're starting to form a lot more glomalin and sugars in the soil underneath, which is really what we're chasing as far as soil aggregation. And this is a no-till system as well. Nice friable soil underneath. And a really good barley crop on the left, which unfortunately we didn't get a yield on because the header caught fire. This was an example of the program. So we had 6 litres of Precede, 5 litres of Nutrisoil, which your loam could go in with that as well. Some Pearl A, 100 kilos of Pearl Surge, which is our combination of coated urea and ammonium sulfate. So it's actually less nitrogen applied, but you're getting that sulfur in the plant to help convert as well. And then a custom foliar, which contains some cal nitrate and those conversion elements. Lockout liquid, which was another hit again of bacillus and some trichoderma. And that meant that we didn't need to apply a fungicide on our yellow bow wheat, which has mild resistance anyway. So that kept it at bay. And we didn't see rust in that paddock, which was excellent. And then a flowering foliar to finish without potassium. That's what the program looked like. And this is just down the road as well. Nice picture of how the barley finished, 7 tonne to the hectare last year, considering the rain, which I was quite happy with. And this is what that program looked like. It was a little bit more intense. So a couple top dresses of Pearl Surge, which is 32 units of N instead of the 42 in 46 in Urea. And it's much the same as the prior program as well, but it's just an example of how we put our recos together. And often it's a case-by-case basis based on the weather and what's getting thrown at us. This is a SAP test that was taken before on that wheat, where it had the high granule application. So we're trying to convert our nitrate into total nitrogen. We've got low conversion elements, boron, copper, moly. We'll skip to the next one, Bruce. After we apply a foliar containing these, we get a reduction in accumulated nitrates, so improved nitrogen metabolism in the plant. And the molybdenum is a cofactor of nitrate reductase. That's a specific enzyme that it's involved in, and that's how it achieves this process. Lastly, I just wanted to finish with a trend that seems to be happening over the last 5 years, based on all the SAP data we've collected. This is mainly across northeast Victoria and southern New South Wales, just a decline in some of the trace elements and sugars as well. So as we're growing bigger crops, we're pumping up with more nitrates. Our sugar's reducing, and sugar's really important for maintaining our secondary metabolites, which give you those defense mechanisms against pest and disease. And then we'll just skip through these quickly, Bruce. The decline in moly slightly, a conversion element, decline in copper, and a decline in zinc as well as we go along. So just putting them as a foliar is really important for our nitrogen use efficiency. And yeah, that's me having some fun on the road. And I think we're up to the question times as well. So thank you.
Beautiful. Thanks, James. Yeah, the headers don't ever burn down in a drought year in a 1 tonne crop, do they?
They don't seem to, no. Anyway.
No. I just hope we got insurance on that. Yeah, any questions? Yeah, please, you can unmute and ask yourself or chuck in the chat there if there's any questions from James around any of that. We'll also have a bit of time at the end if you have a think about things and let digest it a bit. Nothing straight off hand, I don't think.
Yeah, I just wanted to go and give you an overview, and we can always be more specific as we do another webinar.
Yeah, definitely, James. Thank you. All right, well, we might pass across to Dr. Anders Claassen, mycologist at Loam, who has stepped in today to present. So have you got... yeah, you're all good to go there, Anders. You're on mute.
All right, all good. Am I driving?
Yep, you're driving, mate. Take it away.
G'day, everybody. My name's Anders. So I am a mycologist here at Loam Bio, and the work I do here informs product development and commercial strategy. Work extremely close with fungi, so as suggested, if there are any questions about what loam products are or how they work, please feel free to reach out either to me directly or in the Q&A here. So for just a bit of context before I start showing you slides, fungi don't fix nitrogen, obviously, but they play a very fundamental role in nitrogen dynamics in cropping soils. So a typical hectare of cropping land might have somewhere in the vicinity between a few hundred kilos to a tonne of fungal biomass. And so it's not trivial. The biomass itself of fungi is an N sink. So it's good to get that out in front. And while it's not mineralized yet, that N forms a massive driver of processes downstream of the crop development cycle that liberate N again and make it bioavailable to crops fungi are also extremely important in aggregate formation. And so fungi drive aggregate formation processes through some of the mechanisms that James has just elucidated. And it's within mineral protected aggregates that N can be banked and prevented from loss over the long term. Finally, fungi form an intricate and complex network through soils, as you're probably aware. And it's that network of fungal filaments that acts both as like a sponge and like a net. So fungi are one of the key features of highly functional soils that prevent leaching of N, and that also mitigate N loss through volatilization as gas. A lot of the terminology and descriptive terms that are used to describe Loam's bioinoculants are kind of in alignment with AMF, so our arbuscular mycorrhizal fungi, which almost everyone is familiar with. So we borrow some of those mechanisms and terminologies for ease of explanation, but there are fundamental differences in Loam's products that give us a distinct advantage in terms of the resilience of these microbes and their applicability and versatility across a range of cropping contexts. By means of the mechanism, carbon will come in through the atmosphere and enter the plant through its respiration processes. Some of that carbon will be partitioned to the root zone. And as already described, those carbon-rich root exudates will interact with fungi in the rhizosphere that we have put in place. And then those fungi extend out beyond the nutrient depletion zone and into the bulk soil, where microaggregates are formed. And it's in those microaggregates that fungal filaments can be locked up long-term. At a finer scale, carbon binds to the surfaces of minerals, and it's in that context that carbon can be mineral bound as mineral associated organic carbon and be stored long term. A lot of people are familiar with different fractions of carbon, but just as a refresher, we have particular organic carbon, which is that fast cycling kind of plant derived carbon that's like the detritus that decomposes in days to months, depending on your moisture and temperature. A more stable fraction is the aggregate carbon, and that's carbon that's kind of physically contained within soil aggregates where it's not exposed to microbes and oxygen. And then finally, the mineral associated organic carbon, as I've just described, is that carbon that's bound to those clay surfaces, and it forms kind of the largest and the most stable pool that underpins long-term sequestration and soil health. This is what our fungus looks like up close and personal under the microscope at about 400x. This fungus went into dry soil. Everything looks moist because the fungi are wicking moisture from the ambient humidity in the atmosphere. The fungal filaments are proliferating among those disparate soil particles and really pulling them together and binding them together into microaggregates, which downstream will form macroaggregates. These are the processes that really help to kind of synergize soil structure in such a way that is beneficial for crops. It's not a straight line between adding a fungal inoculum and increasing your long-term farm productivity. The fungal inoculum through these processes drive the soil aggregation, and by aggregation we're able to build more carbon and bank more nitrogen and increase long-term farm productivity. So it's really the co-benefits of using fungal inoculum that are independent of the carbon build, which was our original value proposition here at Loam. Those include obviously increased soil aggregation, enhanced nutrient use efficiency, and water use efficiency as well. And it's through kind of stimulating those processes that we get enhanced carbon outcomes downstream. Those outcomes have been really favorable for us and they've allowed us to commercialize a range of products depending on different needs and application formats, be they seed treatment, be they through air seeding in the furrow-mate unit, and also for pulse crops as well. We have a range of commercial partners that we work with in universities as well. And I'll walk through some of the data that's been associated with some of these institutions and what we've found through collaboration and third-party analysis. Here we have a comparison of two trials, one that was done at Western Sydney University and the other at UQ. The Western Sydney University work is a wheat growth chamber trial, and we have significantly increased both total nitrogen and the amount of nitrogen that's held in the aggregates that were analysed in that pot trials are fine, but how does that translate to the field? And in the UQ trial here, which is using soybeans, we came out with about 20% more total nitrogen and over 56% more nitrogen within soil aggregates. So obviously when you see similar outcomes that are reflected both in controlled environments in the glasshouse and then in the field, that suggests that we have some robust data and a real thread to pull on here. So this is a soybean trial, field trial that CSIRO undertook at the Gatton Research Station. And we were able to achieve here up to 11% higher levels of carbon in soil compared to plants without the fungi. And the important thing here is the nitrogen kind of increased with the C stock in a linear kind of monotonic fashion, which is really reassuring. In multi-year strip tiles, here we have Palomaloa here over barley, canola, and wheat over 3 years. Then it falls, we had canola, wheat, and barley. And both of these 3-year long-term CarbonBuilder trials have had a really positive ROI. So average annual yield uplift was about $70 per hectare per year, with a net return of about $45 per hectare per year. So the best yield performance here occurred at both sites during 2023 when water was limited. And yeah, the 2024 Pali canola trial was deficient in N as well. So interesting multi-year data coming out from the field. We've had Optosoil, third-party collaborator who's measured plant available nitrogen across 3 trial sites post-harvest in January 2026. So in this work, fertilizer rates were held constant for the treated and control strips across all sites. And the primary variable here is CarbonBuilder application history. So at Forbes and Palomaloa had received 3-plier applications, 2023 to 2025, while Balata received its first application at sowing in 2025. So quite an impressive jump. So I'm sharing here independent small plot trial by the Grower Group in Riverina Plains. They've dubbed this the Microbial Olympics, and we can't reveal obviously the brand names of the competitors, where we can show what was in them. And this essentially pitted CarbonBuilder wheat against 5 other root biostimulants. This is run near Wagga Wagga, and it's pretty cool. It's essentially a practical head-to-head amongst microbial biostimulant options, and CarbonBuilder at the end there finished with the highest mean wheat yield in the whole set. So importantly, this isn't just CarbonBuilder versus nil. This is CarbonBuilder against other biological concepts that growers would, realistically compare it with. Jumping over to fractionation and being able to shift those fractions in a favorable direction. Here we can see at Pallamalawa, New South Wales, we have fractionation after 2 years of CarbonBuilder application, 2023 barley and 2024 canola rotation. And we've had a jump in the aggregate C fraction there, and you can see the MAOC beneath that fraction is also elevated. And at Forbes here, we have a 2023 canola, 2024 wheat rotation. And again, we see a really favorable jump. Okay, so at Ballada here, New South Wales strip tile, looking at yield over soil type. Here we have a kind of gradient and a declension of heavier soils through to lighter soils. And so Outlook Ag performed the RGBI index here to separate the heavier from lighter soils that you can see here over on the right. And some of the key messages coming out of this data is we had increased yield in lower performing areas of the paddock. And in low rainfall, we had increased yield in lighter soil. In high rainfall, in heavier soil, it implies kind of nutrient efficiency or stress mitigation effect rather than some kind of blanket productivity uplift. But again, it's favorable. So we're getting kind of a bump in yield over control here in canola and wheat. And to round this stuff off, I know there are a lot of concerns out there about compatibility. It's quite topical at the moment. I want to think particularly about something like Vitrato, Vibrance, and Thyram, and the kind of effect that seed application of fungicides and other agrochemicals can have on the performance of fungal inocula. Our Pharamate platform allows us to place microbial inoculum outside the hot zone of seed applied agrochemicals. And so we really have a opportunity here to pursue a way to get inoculum into cropping systems that mitigates those kind of compatibility issues. And that's something that Loam is investigating pretty strongly at the moment. And some of the assays that I'm developing that are coming down the pipeline will examine this directly and inform us as to whether we can actually successfully put inoculum outside that blast radius of these hot chemicals that would really limit the effectiveness of these products in the field. And so it's an extremely exciting avenue for research. I can also speak to other issues that are topical at the moment, particularly dry sowing and those kind of things. So if anybody has any further questions, please reach out, and thank you for your attention.
Anders, there was just one question there. What do you find are your top 3 fungal killers in Australian ag systems?
In terms of agrochemicals?
Yeah.
Well, my experience with flutriafol's always been pretty bad. The chemicals are obviously entering a level of sophistication now where they're kind of multi-locus. They work on all these different sites in fungal biology. So it's not the case anymore that you can drive mutations kind of around the activity now. So we need broad spectrum solutions to kind of mitigate compatibility issues. And I think Pharamate is certainly, from my perspective, a breakthrough platform in that respect, because it changes the conversation altogether. And it lets us put inoculum in a place where roots have exited the activity window of those seed applied fungicides and then have access to the fungi when they break out the other side. And that's pretty simple and elegant to demonstrate. I'm looking at Vitrato Vibrance at the moment, both individually and combination, but any kind of hot fungicide that's in the same kind of class as the triafol is going to smoke them out. Yeah.
Cool. Were there any other questions? Here we go. One. Yeah, are you continuing to also explore adding your product without the addition of the fungicides if take faith to embrace the benefits of protection due to increased diversity of community, not still fearing pathogen prevalence versus activity?
Yeah. So one of the key issues that fungicides presents to microbial management is that the broad spectrum fungicides are going to really kind of destroy beneficial microbes as well as the pathogenic microbes. So where an RDC might give decision support on having soil tests that determine arbitrary thresholds of pathogens prevalence in the cropping soil, and then give recommendations on if your levels are above this certain threshold, then you might expect a yield penalty of X. It's on this basis that we use these chemicals, and what they can do is that they can actually reduce the activity of beneficial fungi, particularly in the rhizosphere. And many of those fungi produce antagonistic metabolites and have buffering mechanisms against pathogenicity. Simple biological reasons for that. They occupy the same ecological niche. And when you get rid of them by adding some of these chemicals, you can actually compromise your yield projections to a degree that's kind of worse than the pathogens themselves. In other words, you throw out the baby kind of with the bathwater, and I think it's a very interesting question to see what these systems would look like with and without fungicide under different thresholds of pathogenic pressure. Those are questions that are very interesting to explore. Yes.
Okay, thanks, Anders. And thanks, James and Bruce. Yeah, we might finish it up there unless there's any more questions from the call. I don't think there is. Well, I hope you found today useful. Yeah, just a reminder, this webinar has been recorded and will be sent out so you can watch or listen when you want, and also share with someone else. And yeah, we just encourage you to, if you have any further questions, to head to the Hybrid Ag website to get in touch with Bruce or James, or have a look at their offerings, or if you want any more information. And likewise to the Loam website for any more information on CarbonBuilder, and it's available at retailers. So head to their website, and there's CarbonBuilder for canola, wheat, barley, and pulses available as seed treatment or through the Pharamate, as Anders mentioned. But thanks for your time today, and hope you get some rain in your patch soon.